Welcome to using Riemann sums to evaluate definite integrals. Notice this is evaluating, not approximating. So recall we had our three formulas. So we had for our left-hand rule, the definite integral from a to b of f of x dx was approximately equal to b minus a over n times the summation from I equals 1 to n of f of a plus I minus 1 times b minus a over n. We had our right-hand rule. Which said the definite integral from a to b of f of x dx was approximately b minus a over n times the sum from I equals 1 to n of f of a plus I times b minus a over n. And then our midpoint rule said that the definite integral from a to b of f of x dx was approximately equal to b minus a over n times the summation from I equals 1 to n of f of a plus 2I minus 1 times b minus a over 2n, or you could put that 2 under the 2I minus 1 if you so choose. So these were three ways that we could approximate the definite integral from a to b of f of x dx. So the question then comes, what happens if we let n go to infinity? So if we let n go to infinity, then we're getting more and more rectangles. Of thinner and thinner width. And as we let these rectangles get thinner and thinner and thinner, then the less chance they have for having either for underestimating or overestimating area by very much, right? And so if we think of, I'm going to just draw a few graphs. So if we want to do, I don't need that whole space, sorry. Let's just say we want to do this, and then I'm going to do a few copies of this. All right. So if we think of breaking these into a series of rectangles, right, maybe going from here to here in rectangles, I'm going to use the right-hand rule because it's easier. So if I use the right-hand rule, these rectangles, we have some overestimating, some underestimating. They're not perfect. The area is not going to be exactly what we are looking for. Now let's go ahead and do slightly narrower rectangles. Again, using the right-hand rule. And this time around, those little triangles or almost triangles of either extra or underestimation are much smaller, and we're getting closer to actual area. So now again, we're going to go even tinier. I'm going to need to use a smaller point. Going even tinier. When we do these extra little rectangles, the area is getting even closer to actually estimating the precise area. So if they went smaller and smaller and smaller, we should get closer and closer and closer to actually estimating the area. I'm getting sloppy now, but you get the idea, right? So the approximation will get closer and closer to the actual definite integral. Oops. So we have the approximation gets closer and closer to the actual definite integral. And what we wind up getting is that if we take the limit of any of these formulas as n goes to infinity, we wind up getting the actual definite integral. So we wind up getting for each of these formulas, if we take the definite integral from f of x dx, or the definite interval from a to b of f of x dx, this is equal to the limit as n goes to infinity of any of those three formulas, right? So I prefer working with a right-hand rule because it's easier to work with. So that's what we are going to do. So all we have to do is figure out our summation for the Riemann sum for the right-hand rule for n rectangles, and then let n go to infinity, and we get our definite integral. So we want to evaluate the definite integral from 1 to 5 of x cubed dx using the right-hand rule. So again, our formula, we're going to do take the summation from I equals 1 to n. We'll have b minus a over n times that summation. And then inside we have f of a plus I times b minus a over n. So this is our formula, and then we will let n go to infinity. So in this equation or setup, this is my a is equal to 1, b is equal to 5, and my f of x is x cubed. So we have b minus a is 5 minus 1, or 4. And so what we're looking at is we have 4 over n times the summation from I equals 1 to n of f of a is 1 plus, and then we'll have I times 4 over n. Or in other words, we have 4 over n times the summation from I equals 1 to n of 1 plus 4 over n times I, the whole thing cubed. So we have 4 over n times the summation of from I equals 1 to n. 1 plus 4 over n I cubed becomes 1 plus 12 over n I plus 48 over n squared, I squared, and then plus 64 over n cubed, I cubed. That's just multiplying out 1 plus 4 over ni times 1 plus 4 over ni times 1 plus 4 over ni. So we are looking at, this is 4 over n times, we have the summation from I equals 1 to n of 1, plus 12 over n times the summation from I equals 1 to n of I, plus 48 over n squared times the summation from I equals 1 to n of I squared, plus 64 over n cubed times the summation from I equals 1 to n of I cubed. Each of these summations is one we know. So we have 4 over n times this first one is just n times 1, or n. Then we have plus 12 over n times n plus 1 all over 2. Then we have plus 48 over n squared times n plus 1 times 2n plus 1 all over 6, and then plus 64 over n cubed times n plus 1 over 2 squared. If we multiply that 4 over n back in, we are looking at 4 plus 24 times n plus 1 over n. Then we have plus 32 if I did that correct, times n plus 1 times 2n plus 1 all over n squared. And then we would have plus 128. Oops, sorry. That whole thing's being squared on the right. So we'll have 64. Then we have n squared to cancel out. We'll just have the n plus 1 squared left up top, and we'll have an n squared down below. And then we're going to let n go to infinity. So every single one of these has the same degree up top as down below. So that comes in handy. We just need to figure out what the leading coefficient is. And then we can figure out what each limit is as n goes to infinity. So just a note here. Each term or each fraction has the same degree in the numerator as the denominator. And so we have that the limit as n goes to infinity of each term is just the ratio of leading coefficients. And So I'm not going to multiply the whole thing out. I'm just going to look over the leading coefficients. So the limit, if we let n go to infinity, we will have 4 for the first term. And then the next one would be 24 over 1 for our leading coefficients. Then the next one, we have a 32 times 1 times 2 for our leading coefficient. So we have a leading coefficient of 64 up top and 1 down below. And then once again, we have a leading coefficient of 64 up top and 1 down below. So we wind up with that our definite integral from 1 to 5 of x cubed dx should be equal to 4 plus 24 plus 64 plus 64. And that is what? 28 plus 128, otherwise known as 156. So we wind up getting that the definite integral from 1 to 5 of x cubed dx is 156.